Section 2.5 Linear Functions of Random Variables. In this video, we are going to define the mean and variance of linear combinations of random variables, calculate the statistical properties of joint random variables, and define and calculate sample mean and sample variance, and also relate them with the population means and variance. Remember, the population is a superset that contains the sample. Modifying a random variable. Motivation. In some situations, the variable of interest is a function of a random variable, and we would like to know the statistics of that variable. For example, consider a machine that manufactures shafts of length L. We know the mean and standard deviation of the shaft. Then it's required to change the length of the shaft to L plus B. The question is, what's the new mean and standard deviation? Another example. The temperature in a refrigerator is measured in Fahrenheit. However, the manufacturer provides the information in Celsius. So we have an equation, which is a linear equation, to transform from Fahrenheit to Celsius. But what is the new mean and standard deviation? We will limit our study to the following operations. Multiplication by a scalar. So we have x, and we are multiplying by a, which is a real number. Addition of a scalar. We have x, and we are to add another scalar. And addition of two variables. We have x and y random variables, and we want x plus y. Linear functions of random variables. If a is a random variable and a and b are constants, then the mean of ax plus b is equal to a times the mean of x plus b. This can be observed in the plot on the right hand side, where the location of the mean of the new variable ax plus b is given by the linear combination of the mean. This statement can be easily demonstrated using the definition of the mean. The mean of ax plus b is equal to the integral of ax plus b multiplied by f of x dx, and that integral is over the whole domain. Now, using the linear properties of the integration, we can have that this integral is equal to a multiplied by the integral of x multiplied by f of x plus the integral of b f of x dx. We can recognize that this is the mean of x, so we have a multiplied by the mean of x plus b, the integral of f of x dx, which is equal to 1. So this is a mu of x plus b multiplied by 1. Now, the variance represents how dispersed is our distribution with respect to the mean. It can be illustrated by looking into the thickness of the distribution. So I have plotted the original distribution, and I have in green and in orange two distributions. We can observe the thickness of the distribution, the one in black and the one in green. So the one in green has a larger variance, and the one in orange has a smaller variance. Now, the variance of ax plus b is equal to a squared multiplied by the variance of x. If a is equal to 1, the variance will remain the same, but if the absolute value of a is less than 1, the variance will be smaller, and if the absolute value of a is larger than 1, the variance will be larger. More on linear functions. Well, if x and y are random variables and a and b two constants, the mean of ax plus by is equal to a multiplied by the mean of x plus b multiplied by the mean of y. And in general, if c1 to cn are constants, the mean of the linear combination, that is c1x1 plus c2x2 plus cnxn, is equal to C1 multiplied by the mean of x1, C2 multiplied by the mean of x2, and so forth. That's a linear property. Now, if x and y are independent random variables and s and t are sets of numbers, then the probability that x is in s and y is in t is equal to the probability that x is in s multiplied by the probability of y in t. In general, if we have x1, x2 to xn independent random variables, then the probability of x1 in s1 and x2 in s2 and so forth is equal to the multiplication of the probability of x1 in s1 times the probability of x2 in s2 and so forth. Variance properties. In general, if x1, x2 to xn are independent random variables, then the variance of the sum of x1 plus x2 plus xn is equal to the sum of the variance of x1, the variance of x2, and so forth. In general, if c1, c2 to cn are constants, then the variance of the linear combination c1x1 plus c2x2 plus cnxn is equal to c1 squared multiplied by the variance of x1 plus c2x squared plus the variance of x2 and so forth. This is not a linear combination. In particular, we have the variance of the sum and the difference of random variables x and y. So the variance of x plus y is equal to the variance of x plus the variance of y. But the variance of x minus y is equal to the variance of x plus the variance of y. It does not subtract in this case. Independence and simple random samples. So these are a couple of definitions to finish with this section. If x1 to xn is a simple random sample, then x1 to xn may be treated as independent random variables, all with the same distribution. Also, when x1 to xn are independent random variables, all with the same distribution, we sometimes call x1 to xn independent and identically distributed. Finally, the properties of the mean of a sample. If x1 to xn is a simple random sample from a population with mean mu and variance sigma squared, we have that the mean of the sample is equal to the mean of the population. Now, the variance of the sample, it will be equal to the variance of the population divided by n, and n is the size of the sample. Now, the standard deviation of the sample will be equal to the standard deviation of the population divided by the square root of n.